Today we are going to study the second chapter of reservoir engineering, which is permeability. So permeability is a property of the porous medium that measures the capacity and ability of the formation to transmit fluids. It is represented by K. Permeability can be defined by Darcy laws. So what is Darcy law? It can be, say, with respect to velocity and also in terms of flow rate. So it is V equal to minus K divided by mu dP by dL, where dP by dL is a pressure gradient. In this formula, V equal to minus K upon mu dP by dL, the V represents apparent fluid velocity and K is permeability, which is in Darcy's. Mu is viscosity of the flowing fluid, which is in centipoise, and dP by dL is pressure gradient. If we talk about the flow rate formula, Q is in centimeter cube per second, A is in centimeter square. Generally, 1 Darcy is high permeability because most of the reservoir have less than 1 D permeability, and let's say they have permeability in millidarcies. So for linear system, if we are going to represent the Darcy law, it is Q equal to Ka P1 minus P2 divided by mu into L, where this arrow represents the flow direction. It is the length of the reservoir, width, height, and corresponding pressures P1 and P2. Q is constant for the liquids because density does not change significantly with the pressures because liquid have less compressibility. The negative sign in this Darcy law is necessary because as the pressure increases in a particular direction, length will increase in opposite sign. That is, we are defining the permeability. It is the absolute permeability. And here's again a term comes horizontal permeability and vertical permeability. Horizontal permeability and vertical permeability can be defined as core cuttings. When a core sample is obtained by drilling parallel to the bed planes, that is parallel to the flow direction, then that permeability is called horizontal permeability. Here we can see that horizontal permeability can be defined by horizontal core cuttings. So horizontal permeability can be represented by KH. The measured permeability on plugs that are drilled perpendicular to the bedding planes are referred to as vertical permeability. The vertical permeability, as we can see, Kv is a perpendicular core cutting. It can be represented by small kV. If we talk about the validation of the Darcy's law, or we can say when we can apply the permeability formula, so here are 3 conditions: laminar flow, no reaction between the fluid and the rock, only single phase present at 100% pore space saturation. We can also say this is the absolute permeability. If we can see the definition of the absolute permeability, it is that the permeability at 100% saturation of the single phase is called the absolute permeability. So it is a definition of the absolute permeability. If we are going to define the permeability for the dry gases, because the core sample can be tested with the dry gas or it can be tested with the liquid. In using the dry gas in measuring the permeability in the lab or in dry gas reservoir, the gas volumetric flow rate Q varies with pressure. The gas is highly compressible fluid because. So in the case of dry gas, the value of Q at the average pressure in the core must be used. So P1 Q1 equal to P2 Q2 equal to PM QM. PM is the mean pressure and it is the average of P1 plus P2 divided by 2. The gas flow rate is usually measured at the base or atmospheric pressure. Then QGSC PB equal to PM QM, where QGSC represent the flow rate at the standard conditions. PB is the base pressure, which is considered as atmospheric pressure. So if we put the formula from the Darcy's equation, QM, So Qm is Ka P1 minus P2 divided by mu g L, and Pm is the mean pressure. So QGC becomes Ka P1 minus P2 divided by mu g L Pb P1 plus P2.
The second most important term for permeability is Klinkenberg effect. The Klinkenberg experimented two core samples of the same field. Then he observed that the permeability of a core sample measured by the flowing air is always greater than the permeability obtained when a liquid is a flowing fluid. So Klinkenberg also postulated that the liquids had a zero velocity at the sand grain surface, while gases exhibits some finite velocity at the sand grain surface. That means the gas exhibits the slippage at the sand grain surface. The slippage resulted in a higher flow rate for the gas at a given pressure differential. Klinkenberg also found that for a given porous medium, as the mean pressure increased, the calculated permeability will decrease. So here is the formula for the gas permeability. So Kg equal to Kl plus C 1 by Pm, where Pm is the mean pressure, C is the slope of the line, Kl represents the absolute permeability, Kg is the gas permeability. We can draw the permeability versus 1 by Pm graph. Here, when 1 by Pm is 0, this means that Pm is infinite. So if we talk about the gas, when Pm is infinite, that we are going to compress the gas in infinite times. So at that time, the gas permeability and the liquid permeability will equal. They will meet at the y-axis. The gas permeability shows a steeper slope, while the liquid permeability represents a constant when we draw the permeability versus 1 by Pm graph. Going forward, when we are going to draw the air permeability versus 1 by Pm graph for different permeability reservoirs. So it shows that when the reservoir permeability is too low, then the graph is less steeper. And when intermediate permeability, then more steeper than lower permeability and corresponding high permeability. For different gases, when we are using different gases in the laboratory for core permeability measurement, then we are going to take the methane as a steeper slope, ethane less steeper than methane, propane the least steeper slope for that laboratory experiment. When we are going to calculate the permeability, so here's the C. C represents the slope of that line and equal to BKL, where KL is the absolute permeability. As earlier said, B represents the constant, depends on the size of the pore openings and is the inversely proportional to radius of capillaries. It's most important data that B shows. Coming forward to the formula, Kg equal to Kl plus BKL 1 by Pm. P is defined as B equal to 6.9, Kl minus 0.36. And then equation becomes 6.9 Kl 0.64 plus Pm Kl minus Pm Kg equal to 0. There are different geometries in the reservoir. These are the simple geometries which we are going to discuss. So the first geometry is linear flow through the layer beds. For calculation of the permeability for these types of reservoir, we can add the flow rate of each layer. So Q total equal to Q1 plus Q2 plus Q3. The pressure difference is P1 and P2, that is inlet pressure and outlet pressure. Q1, Q2, Q3 are corresponding the flow rates of the different layers, K1, K2 and K3, respectively permeability, and H1, H2, H3 shows the different heights. L will be the same, width will be the same. So K average equal to K1 H1 plus K2 H2 plus K3 H3 divided by H1 plus H2 plus H3. By this formula, we can define the average permeability. If the area is different, that means the first layer has different area, second layer has different area, and third layer has different area. So then we are going to define the K average is K1 A1 plus K2 A2 plus K3 A3 divided by A1 plus A2 plus A3. When we are defining the harmonic average permeability, so we can add the pressure difference of each layer, because here the flow rate will be the same for each layer. So if the layer length is L1, L2 and L3 respectively and width is W, pressure differential is delta P1, delta P2, delta P3. So delta P equal to delta P1 plus delta P2 plus delta P3. So K average becomes, for harmonic, L by K1 plus L by K2 plus L by K3. Similarly, we can define the Darcy's equation for radial flow. So for radial flow, the flow rate formula becomes Q equal to 2 pi Kh Pe minus Pwf divided by mu ln Re by Rw, where Re is the drainage radius and Rw represent the wellbore radius. For different permeabilities of reservoir, we can define the formula as K average equal to ln Re by Rw summation ln Rj divided by Rj minus 1 Kj. If we are going to define the geometric average permeability, it is the K average exponential of summation I equal to 1 to n h1 ln Ki I equal to 1 to n hi. If all sample has same thickness, then the formula becomes K average equal to K1, K2, K3 up to Kn to the power 1 by n. Let's discuss some questions based upon the permeability. These are some questions which can very well relate to the formula which we are discussed. So, calculate the permeability of the core, length 20 inch, diameter 2.4 inch, air flow rate 30 cm cube per second, inlet pressure 20 psi, outlet 1 atm 14.7 psi, air viscosity 0.01984. Here we can say that the experiment is based upon the air. So we are going to calculate the air permeability. Here we can see the P inlet equal to 10 plus 14.7 divided by 14.7. Here we will take the 14.7 because it is atmospheric pressure and inlet contains the atmosphere. So when we will divide the 14.7, it will convert to 1.68 atm. P outlet is in atm, so 1 atm. Pm equal to P1 plus P2 divided by 2. It is the mean pressure, so it is comes 1.34 atm. Length equal to 20 into 2.54. This 2.54 is because of inch to centimeter conversion. Area becomes pi into 1.2 to the whole square divided by 1 divided by 2.442 whole square. This is because of the inch to centimeter conversion. It is in centimeter square. So when we will apply the formula for the gas, so there is a Ka P1 minus P2 L mu G Pb P1 plus P2 divided by 2. This is the gas permeability formula. So here Pb, as earlier stated, is the atmospheric pressure or base pressure, so it will be the 1. So answer comes 113.5 millidarcy. The permeability of the core plug is measured by air. Only one measurement is made at a mean pressure of 2.152 psi. The air permeability is 46.6 millidarcy. Estimate the absolute permeability of the core sample. So this is the question for the Klinkenberg effect. So the actual absolute permeability is 23.66. We have to compare to it. So if we write the Klinkenberg equation, it is Fki equal to 6.9 Kl to the power 0.64 plus PmKl minus PmKg. So if we put the value of Pm and PmKg, so it will become like this. If we differentiate F dash Ki equal to 4.416 Ki to the power minus 0.36 plus 2.152. Newton-Raphson method is an iterative method, so we have to iterate it. So Fki equal to 6.9, 30 to the power 0.64 plus 2.152 multiplied with 30 minus 2.152, 46.6. if we solve it, then it comes 25.1192. If we put the value on f dash ki, so it will comes out like 3.45. If we apply the formula Newton-Raphson method, then K2 becomes 22.719. We have to iterate it until the value will not going to be changed. So we apply 3 times Newton-Raphson method, then we will get the 22.86. Then it is not going to be changed. So we don't have to apply that formula again. So if we compare 22.861 with the given value 23.66, so here is the minor difference. So here we can say we have successfully applied the Klinkenberg effect and Newton-Raphson iterative method. So that's for this permeability lecture. Hope to see you again.